All right, welcome back, everyone. This is officially the start of the next session, which is modeling interstellar forces with links. Okay, so what you're gonna learn in this module is to how you can connect the center of mass of two cells. It can be a cell, it can be a compartment within a cluster, and you can associate a force between them, two links, and then you can have a motor force between multiple cells, and you can use this to drive out sorts of um, uh, morphogenic processes that change the shape and behaviors of cells and tissues, or sets the stress relationship of your cells to the formation. Okay. So what you're seeing in the back is a bunch of cells of different types linked together. You can specify the number of links per cell or links per cell per type. Okay. And that's what you're going to be seeing today in this module. Okay. Remember this, we are on Zoom. So you can, there the Zoom logistics. Here's the tentative course outline. Okay. We are here on day 6. We have seen lipid compartment cells. That's module. Here we start with links and FPP, okay? But before me going into how you actually implement those links between cells so you can generate forces or make the cells more rigid or more soft, let's go back to the previous let's go back to the we didn't quite complete the previous module. I left you guys with an exercise about how to choose the contact energies to make a stable epithelium. Let's revisit that very quickly before we move on to the cell forces. So on the last module, I left you with this exercise. Okay, we have a code to create an epithelium and to merge them together. Okay, so this belongs to the same cell cluster. This belongs to the same cluster, but this structural class belong to different cluster. And the challenge is, okay, how you should choose those energies values here. So did anyone was successful in solving this problem here? It seems that Kishore was able to do it. So, but everybody can see the chat, and Vikram got it. One thing that I can tell you is that sometimes you cannot tell if the boundary you see is from the cell or from the or is a cell boundary or is a cell cluster boundary. Okay, so there's a way to fix this. Let me just, I guess, if you're seeing this video of the crawling cell, let me make a zoom, right? You see that you have boundaries everywhere, but if you go to the visualization, you also can have an option for cell borders. Okay, and if you click on the tools and go to cell colors, you can choose a color for the cell boundaries and a color for the cluster boundaries. So for example, I may want to make my cluster boundary to be magenta, okay, and my cell boundary to be uh, let's say black, okay. I hit okay, and what you see now is that not sure if it's really visible. Maybe I should choose another, but you should see that is magenta here around the cells. So this maybe a bad example because I don't have a cluster yet. Let me open exactly this example. So here now, I set my cell boundary colors to be white and my cluster boundary to be black. Maybe I can choose another one. Let me choose something that's very visible, yellow, okay? hit OK. And then you can see, okay, the yellow boundaries are the cluster boundaries, and the white boundaries are the boundaries within the cluster, within the cells. So you can clearly tell who belongs to whom. What I like to do when I'm using cell compartments is to not have the boundary between the cells, only have the boundary between um, the clusters. So I usually choose this out, and then you see here that you don't have a boundary between all the red, the green, the blue compartments, because that indicates right that they belong to the same cluster. And I think this is a better visualization. And then uh, I also like to have the cluster boundary to be black, so you can have the same thing on the screen. Um, I like this choice. So where you see a boundary is between, so you can clearly see that this belongs to the same cluster, and those two here belong to the different clusters. Or if you want to highlight that even more, you can make the cluster boundary color to be white. Okay, and that's another choice that highlights, okay, these are the cells, these are the compartments, and this is the cluster. Okay, so but that's a minor thing, just to show that you have this kind of choices. So let's go back to the exercise. So how you go about making a stable epithelium, you have to make a choice about which ends should be high, ends should be low. Let's start with the contact internal, okay? So we want the internal compartments to be cohesive. So you probably want the apical lateral, apical basal, and basolateral to have low contact energies. So then they're going to stay as a whole. Okay. If you want to enforce that the apical is say once on the opposite side of the basal compartment, you may increase the apical and basal compartment to be a little bit higher. Okay. So they're going to be the opposite sides of your cluster. Okay. Again, there are no cells with the median or ECM, so we can ignore all those values here on the top, on the lateral. Okay. Uh, in this case, you also do not have repeated domains. You don't have two apical sites or two lateral sites or two basal sites in the cell. So that means that everything that lies on this diagonal here can also be ignored. In some cases, you may have two compartments at the same time in your cell. For example, if you want to model a cell with two nuclei, that may happen, okay? Uh, Either because of disease or because you do have a nucleated cell that happens in some developmental processes. You have two nuclei, then you have to actually specify the energy here. But in this case, that's all you have to do in the um, internal contact energies. Now let's go to the other side, the external contact energies. Okay. You want to have coupling between the apical, lateral, and basal. So you want the cells to not slide one another from top to bottom, but you want to have they making a line along the horizontal, like. So you want to probably have a low contact energy between neighboring apical sites, neighboring lateral sites, and neighboring basal sites. If you already know that all your adhesion junctions are on the lateral side, you may make this lower and those two a little bit higher. But in principle, you want to make this low, but not as low as the internal. So it's going to be a little bit higher than the internal ones. Okay. So I hope this makes sense. So let's now proceed to what should be the cross, right? Apical to this lateral, apical to this basal, or basal to this lateral, and so what about this cross terms here? So you probably do not want the basal to be touching the apical side of the other cell and vice versa, or even touch the lateral to be touching the base, the apical side or the base of the other cells. We want to enforce the alignment. So in this case, you may make the case, okay, that these energies should be high, okay? So that will, this together with this, will enforce the alignment of our epithelium. And epithelium cells are aligned with one another, okay? So you choose them to be higher. Now, the next thing you want to see, okay, how should it be the contact of those cell compartments with the ECM and the medium? Because you want the apical, let's start with the apical side. You want the apical sides to see the medium and to not see the ECM. So what you do, you have a low contact energy of the apical side with the medium and a high contact energy of the apical side with the ECM on the bottom. So you want this value to be high. You can choose the same principle for the basal side. You want it to have a high energy with the medium and a low energy with the ACM. So we make this high and this low. Again, you don't want to get, in principle, you don't want this contact energy to be lower than the internal contact energy. So it always should be, your first choice to be, even though you choose to be low here, it has to be a little bit higher than the internal ones. Okay. Now, next thing you have to do, okay, what about the lateral side? How it should interact with the medium and the ACM? You usually don't want this to interact at all, so you also keep those two values high. And finally, the contact of ECM with other ECM cells, you should be treating as a continuum, so you can just set this to be 0, okay? And the ECM should never see the medium, okay? So you can also set this the last hint to be high. And once you make this kind of choices, and you see that's only qualitatively, you have to think about the behaviors. You run your simulation, and then you should have a stable epithelium. So if as long as you follow this kind of hierarchy here, you should get it. But just to show an example, if I make this kind of choices, it also works, and you should get something that looks like this. And this code with this kind of implementation can be found on file 6.1.2D zip, and this is going to be from the basis for you to then do the epithelial folding that you're going to learn on module 7.4. But before you can do that with epithelium, with cell compartments, you first have to learn how to add links in the cells themselves without the compartments, and that is the theme of this module. So before I proceed, do you guys have any questions about this part?
So in this case, only the cells in the ECM are dividing, right?
No, the same is not dividing. It's just because I set the contact energy to be
Oh,
to
okay,
be 0, they mix.
okay, okay.
The whole question about forces is actually the topic of this module that we are now with the 6.2. So we'll be talking about forces right now. Okay.
Oh,
Well, the contact energy between cells and ECM are set here. It's going to be this. If that was your question, is that here the apical side does not like to touch the ECM, so it's high. The lateral side also doesn't like it, so it's also quite high. But the basal sides do like the being contact ECM, so this is low, 5. Okay.
I see. Okay, thank you.
Okay. So if you want to know how to do this, add those forces within the apical side that drives a foreign formation, we have to go about how implement forces in CompuCell 3D. So let me switch uh, PowerPoint presentations and go back to this one. Okay, so this is where now officially starting module 6.2. in modern cellular forces with links, okay? And I want you guys to maybe see this video here, which I like very much, which shows the development of the zebrafish embryo. And what you see cell division, you see cells coming together to the center. So they are moving in a specific direction and converging on the center and extending on the other one. And then you see the cells rearranging, make structures, okay? And those structures cannot be achieved with simple cell division and contact energies. The cells have to actually actively pull one another, okay? And so you actually add pulling force between the cells along a direction, okay? And the force has to be between two cells, not can be external force. You cannot achieve this with only cell migration, okay? So this is done adding spring links between the cells, okay? That's how you do this kind of fur formation here. That's why we can drive epithelial mesenchymal transition where the cells rearrange to form rosettes, okay? And this, you can also use this kind of approaches to model cells' elastic properties, and that maintains the epithelium in shape. And then when those forces are compromised, then you have some kind of disease happening, and then in this case, retinal neovascularization, the integrity of the basal layer was disrupted. You break those links between the cells, and it can invade, and bad things happen. Okay. So this module here is breaking to many submodels. Okay, we'll go through the first two ones for sure, because that sets the at least the first three ones we're gonna go through today. If there is time, we can do the last two. But if you don't, there is no time, do not worry, because the files are going to be made available and you can revisit them and learn them by your own. All right, so let's talk about how links work in CompuCell 3D. So the way it works is that you can track the center of mass of two cells. Of all the cells, you can track the center of mass. And the way that those links work is just act as a Hookean spring, which connects the center of mass of two neighboring cells. So this is the center of mass one cell, this is the center of mass other cell. There's a plugin CompuCell called FPP, which is short for focal point plasticity, okay? And the way it works is just a new Hamilton energy term to the effective energy of your cells. And it has the same shape, form as before. You have a lambda constraint that sets the strength of the link, and then you set a target distance between the center of mass of two cells, will be the target, and the sigma here, the sigma prime is this cell and this cell, and this little d here is the current distance between those two cell center of masses, and this is the target distance between them. So the energy term just tracks what's the deviation of your the current distance between the two cells with the target distance between the two cells, and you penalize deviation in either direction by having the square here, and you choose your lattice sites flips to minimize this energy or to bring those cells distance to be close to the target distance between them. So that's how it's done. Okay, so how you can implement that? If you are making a simulation from scratch, on the wizard in the 3D, you just select focal point plasticity, and it's gonna generate the code for you based on the number of cells you have. So the code in the XML level looks like this. You have the name of the plugin, focal point plasticity, and here, this middle code here sets the parameters for each cell type pair that you can have. So if you have just one cell type, it's going to set the interaction between that cell type and that other and the same cell type. So between cell type A and A. or my cell and my cell, okay? So this first tag here, lambda, says the strength of the link. So the stiffness, if you think of this as springs, the stiffness of the spring. The target distance is set how far away the center of mass of the two cells should be, okay? And yeah, that's basically it. And this variable here is the current distance between the cells, whatever, but that depends on your initial conditions, of course. Of course, you also have other things here. This, if you have more than one cell type, you can, for example, you have cell A and cell B, you're going to generate a pair for each combination, AA, BB, and AB, okay? So this is sets what pair of cell types you should have the interaction. And then for this type fraction, you can also specify the maximum number of links that those two cell types can have. So if you're modeling a confluent tissue where in 2D, where cells usually have 6 neighbors on average, and you set this maximum number equals to 1, this means that your cell can only make a force link with one of each 6 neighbors, cannot make with all of 6. If you change this number to 2, then you can actually make links to 2 neighbors, okay? And the 2 neighbors that you're going to make the links first, it depends on the lattice side flip. So if you make a lattice side flip that interacts this cell with the cells that's on the right, that's when you make the link, okay? This other parameter here is going to be the maximum distance that you can have between those two cells. So the cells create a link, and you are trying to minimize that energy so they obey the target distance. But if you start to pull the cell too much far away from each other, at some point this link should break, and this parameter here sets the maximum distance in lattice sites that you can bring those two cells apart before the link breaks. Okay. What else? This These two other comments here is something that you don't have to worry about in practice, but just to tell you what how they work is used to set when two links will form. Okay, if you create a link between two cells, you're basically invoking a new energy. You add a new energy term to your system, right? And usually those cells are not start at the correct target distance, so you're adding energy to your system when you create the links, okay? So because you're adding energy when you create the links, this is not something that will happen spontaneously. So to overcome the energy barrier, you have the activation energy set to be a negative number that favors the creation of the links within the two cells. And then the neighborhood is how far away the left side have to be to actually connect the two links together. Okay, so a neighborhood one means that the cells actually have to touch one another before you make the link. If you make a neighboring order much bigger, like 5 or 7, as soon as the cells get close to one another, they can already form the link. Okay. Abhishek, you have a question.
Uh, I missed the part on the negative activation energy. Can you please explain it once more?
Well, as soon as the cells get together, get in touch, you can create a link, okay? But that's energetic unfavorable because you're just adding new constraint, which raise the energy of your system, okay?
Yes.
If the cells are not linked, you don't have that energy term, right? As soon as you have the cells linked, you can now have an energy term. So going from no energy term between two cell pairs to an energy term between two cell pairs, add energy to your system. So to favor the creation of the link, you have to have this activation energy tag here that lowers it in order to create the link. So it's something very technical, something that in practice no one here has to worry about, but just for completeness, I'm just telling you guys what it is because you'll be seeing this code.
Okay. But I think you mentioned that the links maintain the connection even up until the maximum distance, right? That is
Yeah,
20.
you bring a maximum distance, and once it exceeds that, it breaks.
Okay. So in order to maintain the link, they don't have to be in connection, right?
Well, they'll be in contact, right? Well, that goes to what James is writing
Oh,
on the chat. This links has the form of a spring, right? But they can be many different. You can use that to represent many different concepts. It can be Filipodia, for example. In this case, the cells are very far away, and then you can send a Filipo to one to the other and connect and pull, right? That's a case that you don't want to model the Filipodia directly using lattice sites. You just create a Filipodia that you do not see in the system, but the connection is there. Okay, so the cell grab the other cell and pull. Okay, so it can represent that. Okay, so they are not touching. So in this case, you can usually when you do this, you at the Python level, you create the link by hand, okay, and do this. Um, so can also model such skeleton. If you have cell compartments, maybe it's such skeleton inside the cells. If the cells are just touching each other, use the links to represent the cell junctions, tight junctions between the cells, so they don't want to the tight junctions which are usually connect to the intermediate network of intermediate filaments inside the cells. So they keep the integrity of the tissue. If it's a supracellular acting network, you can make the link and decrease the target distance and increase the lambda to model contraction of the cells. So you can use the links to do many different things.
okay. I see. So as James mentioned in the chat, so it is giving the kind of like the cell line of solid-like feature.
Yes, you can also
Okay.
use to do this.
Okay. Thank you. That is.
If you make all the cells connect, you make some like kind of pseudo crystal structure. Then when you apply force on it, you can get some kind of you set what to be the bulk modulus of your tissue or the
I
longitudinal
see.
modulus, the shear modulus. If you slide one
I
against
see.
the other, yeah.
Okay. That makes sense. Thank you.
Yeah. So the cells can have long distance links. All right. So this how it works. So let's see how in theory. Let's see how it works in practice. Okay. So let's create a simple model with links. So please, everybody, open your COMSOL Tweedit. Okay. If you do not want to follow the model creation, you can just download 6.2.1. Because maybe you can already go that because I want to go a little bit fast here. So if you want to do it with me, you're welcome to do it. Let's create a new project, new project, click there, okay? Let's give a name to this module. Let's call it module 6_2_ links, okay? And let's choose Python and XML. Make sure you have the rectangular slab, okay? You can leave those values as it is right now, okay? Cell types, let's create a cell of, give a name to your cell type. I'm just gonna give my cell. Hit add, make sure that your cell type appears here in the table, and then hit continue. Okay, we don't need chemical fields, we can skip that. And here on the cell properties and behaviors, what you need is to have contact, volume flex, center of mass, which is usually already clicked in, but make sure that you have the focal point plasticity option turned on. You need to have this option selected. So once you have those four selected, then you can proceed with continue and you create this. If you don't want to follow the steps, you just can download this code to your computer from the student materials and we have it for you. So once you have this, please run it in your simulation, okay? And tell me what you see, okay? So if you run the simulation, or if you just download the simulation and run, you might see something that looks like this. Did everyone got something that looks like this? Okay. Okay. So you see that on this video here, on this picture that I have here, you can see individual links between cells. I'm not sure I can see those links in the simulation by be sure. So if you don't see the links, you can go to your CompSci player and see that on visualization, you have the FPP links option selected. Okay. So make sure that this has a mark on it. Okay, it didn't load any model, but this part here has to be selected, and then you'll be able to see the links. Okay, and also make a choice for cell colors and cell boundaries, so that your links is easily visualized. Okay, so make so if you click here on this numbers, if your link color is white, don't use white for the cell boundary colors. Use something like uh, black for both, or don't have for anything. And so if the cell boundary colors are black and the link is white, then you'll be able to see them more easily in your simulation. Okay, so let me go back to the. Okay, now Kishore I can see the links on Kishore's simulation, and also Leon, Jupiter, Julio Roar, he completely get rid of the cell boundaries. Okay, so it seems that's working, right? So, but why you see just one link pair and not many? Okay, right, written here. Why is that? Well, if you now open your code on Tweedit and go to the XML file, you see that this maximum rejections is set to 1. Okay, this means that the cells can only make at most one link to the neighbor. Okay, so that's going to be the higher value of links that they have. And usually the cells are able to find a link, but you may have some frustrated cells that could not find a pair, like in this example here. And in your examples, you might also see those lonely cells that didn't link with anyone. I can certainly see one in Jupiter's code. I can now see one in Leon's. They're both on the top right. Another one I cannot see anyone. I can see on the top, on the bottom right, I can see a lonely cell there. Okay, so this is set to 1. So why don't you try to change this? So you can go to your code, or go to uh, the CompSci player if the simulation is running, and you can try to find this value and change to 1, 2, 3, and see the effects. Good question. Yeren asks, so while you do this, I'm gonna answer Yeren question. What's the difference between parameters and internal parameters? Okay, so you see parameters here, and you may also have seen internal parameters. That's the same thing as the contact energy and internal contact energy. Okay, so you have a version for the contact energy for the cells that belong to different clusters, and another one for the cells that belong to the same cluster. The same thing for the links. You have parameters between cells when they belong to different clusters, and the internal one is the same situation. Well, it's the same model, but for when the cells belong to different clusters, to the same cluster. Okay. So question from Susan. The translation into force units is it scales with the force in newtons, but there's not a direct correspondence between the force that you choose and in newtons, because your energy term, you have this kind of noise parameter that you add, okay, which are arbitrary, so you don't have a clear, you don't have direct correspondence between the force that does generate and the unit of newtons, okay? But using doubling the lambda should be the equivalent of doubling the Newton force that results from those links. Okay, this first one here on neighboring order means, okay, how far you only make links once you have a pixel site that make those two cells interact, okay? Neighboring order equals 1 in there, says that they have to actually touch one another to do it. If you have a high neighboring order, a spin fluid that just bring a cell a little bit closer to the other, maybe already sufficient for you to create a link. Okay, so you're at sharing some videos. So you may have seen that this is the first situation 1. That's what happens when you have to set to 2, 3, 4, 5, 6. By the time you set it to 6, all the cells are linked with all the neighbors around it, because in a situation where you have a bunch of cells of the same size together, you have 6 neighbors, right? So at 6, everybody together, and intermediate values, you have this kind of maze happening. Some cells are linked, some cells are not. Okay, some cells, even though you set to 3, some cells might still only have 1 link. Okay, if there's very unlucky cell, some of them will be not linked at all, but that's less likely to happen. And so from this, you can make transitions like rigidity percolation. Okay, so this should be very fluid, also very fluid. So here the cells may be still fluid, and you can still shear it. When you get to 3 or 5, you probably cannot do the shear anymore. So probably you have some kind of rigidity percolation transition as you go from here to here. Okay. So that is what you guys should have seen qualitatively when you play with the maximum number of junctions. So let's try to play something else. Let's try to play now with the target distance between the cells. Okay. Yeah, so yeah, that's going to be a good model for the hackathon. Make a rigid percolation transition using links, right? So let's choose a connectivity level that's low. Use 2 or 3, okay, or maybe even 1. Okay, let's use a low and maximum number of junctions to 2 or 3. And let's play now with this target distance. Do something that's lower than what you expect the cell distance to be, and then do one that's bigger, then do it smaller, and then start to try bigger, bigger, and bigger. Okay. So usually the target distance should be the 2 times the radius of the cell. So the cells are about 7 by 7, right? Then the distance between 2 cells on average will be 7 lattice sites. If you choose a something that's smaller, that has to be under compression. If you choose something that's about 7, which is usually the default, the cells will be already happy on where they are. And now if you choose something bigger, interesting things may happen. Okay, so why don't you play with this and share what you get on the chat? So Vikram, in your simulations, try to choose a very dark cell-cell boundary so you can see the links more clearly. So Kishore, what happened there? What did you do?
Well, with the target distance, obviously, also just moving away to maintain that distance.
So what
And that's
what connective level do you choose and what the target distance did you choose?
target distance is 55.
55?
Yeah, and number of connections is the maximum number of junctions is 4.
4. Okay. Yeah, so your connectivity is along this and you choose 55, the cells just pull each one away, right? But remember that your maximum distance is 20, so probably when they reached 20, they broke the connection.
So the distance is also a number of voxels, right?
Yeah, number of lattice sites. Of course, if you are on diagonal, then you have to. Yeah, 52 will happen. Yeah, that's things like this start to happen. Okay. Yes. Okay, so let me just show the next graph. So if you decrease the target distance, well, everything's going to be kind of a little bit more compressed. It's going to be and if there's some external force acting on the system, it's going to be hard to deform the tissue as a whole, right? If you increase the target distance, now the cells start to be pushing one another. Okay, if everything's connected, you don't see much a drastic effect, but if you have a low connectivity, right, for example, you have a 3 or 2, and you increase the target distance, then you start to see very dramatic effects like this happening. Does this correspond to any biological process seen in vivo? That is up to that I do not know. I have several sea cultural cells that look like that, but the process is usually by some migration and not necessarily cells pushing each other. Okay, but that is just an example to see the sorts of behaviors that you can get by just playing with those parameters. So what you're doing here, we are giving you the tools to do whatever you want. Okay. And you can get things in any model. If you play with the parameters long enough, you may get things that seem unrealistic. And it's up to you as a model to choose do something that looks realistic, looks reasonable for a specific problem. Okay. So there might be a problem that this is the realistic outcome. Okay, but it's up to you. I cannot judge in advance. Okay. Someone got crystals. That sounds nice. And all these changes you can do also on the Python level and do it dynamically. Okay. Can I simply delete the code blocks from medium links? Well, we may have the see if there's a continuum path between one cell and the other, right? That are linked, and if there's a medium in between, you can break the link. But that has to be from the Python lab, if this is what you mean. All right. So I hope you had fun with this. So let's proceed to the next example, where we do a model with two cell types. Okay. So let's create a simulation with links and two cell types, green and purple. Okay. And you either can create this from scratch or you can just download the file 6.2.2.zip. Okay. And then the challenge here is, can you play first do some exercise like make one pair of cells have very short links and the other have long links, and see what that does to your tissue. And the challenge here is, can you come up with a set of FPP link properties that will induce mixing between the two cell types? And next challenge is, can you come up with a set of FPP links properties that will induce the sorting between the cell types? So try to do that with only links instead of using contact areas to do that. So I'll give you a few minutes to do this. Please download the base code and start playing with the links between cells of different types. Okay, seems that Kishore was able to induce separation. Did you also use internal energies or use only FP links, the challenge? That worked very well in our simulation. Okay.
Only the target distance actually.
Oh yeah, the idea is to, I think that you, by your next message that was with contact energies, right? Try to do with only links.
No, this is only with links. With the
With only
target
links?
link.
Oh, that's
Yeah.
excellent. Okay. Try to do the mixing now. So a tip for this exercise is that if you if you keep the maximum distance to 20 as the default, the links will mostly never break. Okay. If you want to have the links to form more dynamically, you can make the maximum distance to 7, which is the typical diameter of the cell. Because then any kind of small deviation from one cell to the other will break the link. Okay. And that's allow for a remodeling of your network, more remodeling of your network. So for both cases, make the maximum distance to be 7 or 8, something that's small. Then you can rearrange the links more easily. Now, Kishore, that you got the cell separation, try to get the cell mixing. You did the hard one first. The mixing, it should be easier. Under got the simulation to work. Okay. Now try to see what happens if they make the green links longer and the purple links shorter, if you see some kind of effect. And then try to do one of those two exercises. Usually self-type mixing is easier. So you can start with this one. So the things that you have to play is the distance, the target distance between the cells, and also the number of junctions between each kind of cell pair. So for some, you want to have lots of junctions. For others, you want to have little junctions or no junctions. You can delete it, Lion, or just set the lambda to 0, because then it'll be ineffective. Okay. Or just set the maximum number of junctions to be 0. Then the junctions will never, the links will never form. The easiest thing to do is set the maximum number of junctions to be 0. Checkerboard pattern. Okay. Do you want me to proceed with the next slides, or want to try a little bit more?
Did you mean me?
Everyone. I see your message now.
I would like it to speed up the simulation, only the simulation, not the talk. And there was something that the Monte Carlo steps are faster, but I don't recall what it was. And I don't know where it was.
Well, one thing that you can do to make the simulation faster is run it in parallel on your computer. So there is a you can make everything smaller. Instead of modeling many cells, you model a few number of cells. And there is also a tag on your cell code, cell code, that you can set the number of processes to use on the computer from 1 to 2 or 4. Okay, that's going to speed up your simulation as well. So maybe one person can talk to you on a breakout room and to show how to do this.
Okay. Thank you.
You're welcome. Okay, so let me show one possible solution to induce mixing. Okay, so if you want to induce mixing only with links, you don't want to have create links between the green pairs and the purple pairs. So not have links between those two, and you do create links between green and purple cells. Okay, and you set the target is to be 1, very small. So the cells, they create the link and they pull on one another. Okay, so the green cell create the link to the purple cell and they pull on another, right? But they don't do the same thing with the other ones. And you set the maximum number of neighbors to be 3, then you get the condition that because the cells in a close packing, they usually have 6 neighbors, right? If you don't allow to make those 3 of those pairs, then you'll be favoring the mixture of things because you don't want the green cell to be completely surrounded by purple cells and vice versa. So you'd make some kind of limit here. And again, with this kind of parameters, you should get this kind of outcome where you have a checkerboard-like pattern between your cells. Negative distance will have no meaning. Okay, I'm not even sure what happens if you do this. I never tried. Well, your distance is always going to be positive number, right? And the negative target distance is D minus D target. If D target is negative, then you always have a positive number. So you always have some energy on your system. So we can reason out from this. Right, so this is the recipe to get mixing. Wow, Vikram got it, excellent. A recipe to get demixing or sorting of the cells is this one. In this case, I don't have links between cells of different types. I only have links between cells of the same type, okay? And I have one of them to have a lower number of maximum neighbors than the other one. So the green ones can have up to 6 neighbors, right? And they have a stronger pulling between another, while the purple one has a lower number of neighbors and they still pull from another, but a little bit less strongly. So what happens is that you have a separation of the two cell types, usually because the green-green interaction is stronger and more contractile. They tend to be at the center of your mixture, while the purple one, because a little bit less strong, and have less connections, tend to go to the outside of the tissue. So these are recipe for cell sorting. These are recipe for cell mixing. Other solutions are probably happening. Also possible. You probably make the green and purple and green cells to connect, but have a very large target distance between them. That would be another way to do it. But these are two possible solutions, and you can download the code that implement them from these two files, 6.2.2a and 6.2.2b. Okay. Is this making sense? The idea behind the distinct one is that the cells are actually pushing on another. They connect and they really want to get very close together. So what's the biology behind this that can justify such a behavior? Then we can question if there is such behavior between cells, but is a way to induce condensation of the tissues. Well, if you're looking at the cells if they are epithelial cells, you're looking at them from the top. Target distance smaller than the radius within the cells, meaning that there's some kind of contraction of the apical site between those cells. So you're modeling apical constriction between them. Yeah, and is there a way to quantitatively evaluate how short the cells are? Yes, there are many possible metrics you can use. The most obvious one is just to compute the boundary between the cells of different types. Yeah, because I'm pushing the cells to be very close together and being squeezed, and this looks elongated. So they are not actually elongating along that, they're just being squeezed in the other. Okay, how about we go to the next set of exercise? So I want to, we can also use these links to model cell crawling, okay, within tissues. So let's move, and that's the idea here. So module 6.2.3, modeling cell crawling with links. You probably have seen cell movement due to chemotaxis, cell movement due to the internal cell propulsion, right? You probably see moves by adding a force to the cells. You have probably seen some movement because they're chemotexing away from a gradient, but here I'm gonna want to use the links to model cell crawling, okay? So the idea is that the cells are inside the tissue, right? So it's a deep tissue cell crawling, and the cells can use the links to connect to the cells that are in front of it and pull out them, okay? So if you just pull them on one side, nothing will happen, right? But if they're gonna push together, but if you can recreate the links if a given frequency, you get then you can get movement of the cell between other cells. Yes, Aaron, that does look sorted. Okay. So let's proceed with modeling cell crawling. Okay. So in the previous examples, we set the initial energy parameters, run simulation, and see what you get. Okay. But in some situations, you want to change those link properties dynamically within the simulation to create new links at will or given some kind of criteria. Okay. This has to be done from the Python level. And the way that you do this is that you have to allow it to happen. So usually the links are not able, you cannot change them from the Python level. But if you uncomment this tag called local inside the focal point plasticity, then this allows you to access the link properties from the Python level and modify them during your simulation. Okay. Okay. So usually when you want to modify the links at the Python level, you don't want the player to do anything for you. So usually when you set the local tag here, you want to make all the maximum adjunctions of all the possible pairs to be 0. So the links that are created are only that you explicitly create at the Python level and not the ones that are otherwise naturally due to interaction of the cells. Okay. So once you have the local tag on and you set all the number of junctions to be 0, you can create new links, access, delete old links, modify the properties of the links, all from the Python level. And everything that you can do will be accessible from the tweeted. You just go to CC3D Python, and there's an option called focal point plasticity, and you click there, and you see that you have all these options that you can choose from. Okay, the ones that you'll be using will usually be the link management, create FTP link. Okay, so this is how it works. It adds this line, of course, so this is just one line. Okay, link create self.new FTP link. This is the cell that creates a link. This is the cell that receives the link. That's going to be the lambda distance. The fourth value going to be the target distance. And the last value going to be the maximum distance that the cells can have before the link breaks. The other thing you may also want to do, you want to delete all the links attached to a cell. And then you just have to do self.remove all cell FP links. And then you just specify the cell, and then all the links associated with the cell are going to disappear. All right. This one here, you have to know which cell want to do this. For the creation, you have to usually have a iteration between the cells of given type and a second iteration between its neighbors, and then you choose the neighbor of the cell, and then you add the link between those two, because you need to know the two cells that you're linking. Okay. So how can you do this to model cell crawling? Usually when you think about cell crawling, and if you read many papers, is a cell walking on a substrate, okay? But this is very artificial, right? Usually the cells are walking along other cells. So what the video you see here below, well, it's a little bit like this. Is one example where the cells do something that looks like this in vivo, where you have this lateral line cells It's just a bunch of cells that originate here and start walking on the surface of this other tissue, just like what you see in vitro experiments. Okay, so this is a case where the cell is actually walking like that, okay, on a surface by creating adhesion sites and pulling on it. Okay. But usually the cells are walking between other cells, and you have deep tissue cell migration. And here the cells, the way they do, they throw filipoda and lamellipoda, and they are pulling the neighboring cells to actually move towards their desired place. So here's a video of neutrophils in GFP and macrophages in red RFP label. Okay, so you want to do something that looks like this. Okay? Because this is happening by cells moving on top of one another, the way you can do this is by having a specific cell in your simulation that can create links in front of it, pull the cells, get moved, and then delete those links and create new ones by grabbing the cells that are further away in front of it, and then make this series of pulling, and then the cell can crawl from one side to the other. Okay. So to create this, we can go over all these steps here to create a simulation from the start. I think for time consideration, let's just download the file 6.2.3a, where all this has been already implemented, and basically you made a simulation with a cell type red and a cell type crawler, and actually don't leave that file now. Let's just skip to this file 6.2.3b, where you already have everything set up in a simulation where you have a confluent a number of cells of type red, okay? And all you need to do, you want to specify a cell there that is of type yellow, okay? So actually, you can even skip this file and let's go directly to 6.2.3c, where you already randomly select a cell. Actually, you do select the cell on the left side to be the side type crawler. So if you download this file version here, you should already get a simulation that looks like this. Okay. So please download the file 6.2.3c, and check when you run your player if you get something that looks like this. So please download this file. So in this file, the cell is not yet moving. What you're going to do next is create the links. Okay. Yeah, so you should see a yellow cell within the red cells and more to the left. And what you're going to do now, you are actually going to use the links to make the cell move. Okay, so I trust that everybody was able to download the link, this base file. So with that, let's just open and all of you should get something that looks like this, and the cell is just random walking there. Have exactly the same characteristics as the red cells. So what I want to do now, let's go to the code and implement this kind of model here. So the first thing to do is add some global variables that you control this kind of properties of the cells. So on the Python file, the steppable files, let's create this line here, global maximum angle, lambda, target distance, and maximum distance, okay? And this maximum angle is going to be how much the cell, you want to throw the cells in a specific direction, but you also should allow some kind of plus or minus in the angle around this. So let's set this angle to be 50 up and 50 down, 50 degrees up and 50 degrees down. You can change this. Lambda is going to be the force of the links, the force of the pull. Let's set it to 2. The target distance, let's set to 0, because when the cell make the links, I want to pull all the way in, okay? So let's set the target distance to 0, and let's say set the maximum distance to be 1,000 lattice sites, meaning that the links will never break unless we tell them to break. So let's just add those 5 lines here to the top of the code. So once you have this, let's do another modification to the code. Let's go to grab the cell crawler and create new links to it. So what you want to do is that on the step function, okay, we add those lines here. So we first check if the Monte Carlo step is higher than some value, and every 50 Monte Carlo step, you want to create new links. Okay, so what you're gonna do is we have this condition here, and first we allow the cell to move a little bit, relax their boundaries, and then every 50 Monte Carlo steps, you're gonna delete all the links that the cells have and create new links. So this line 26, 27 will be just functions. They're gonna do this for us, okay? We have one function to delete all the links that it has, and another function to create the links. And you're gonna write, define those functions in the next slide. Hi, Abhishek.
Yeah, so I have a question. So why did you set MCs to be greater than 5,000? Is there any
I want the
specific?
cell to relax its boundaries first before I make the
Okay.
links.
Oh, okay.
Just like some relaxation time. No, this command will be just for the crawler cells, okay? So that will be defined inside each one of those functions. So here I already showing how to properly code. So if there is something that you have to do very often, and you may do that for many cells, it's better to create a function for it and define this function outside. This way your code will be more easy to read. So once you add those 3 lines inside your step function, okay, it's time for us to define what this delete function will be. So that's the next slide here. We gonna define this. So on line, let's say 29, let's create a first annotation and make a functions def definition, delete underscore link self, okay? And inside this, we create a loop for over all the cells of type crawler, because we want to do that for the yellow cell. And inside that, we add that code that all the links are associated with that cell. So we add self dot remove all cell FPP links, that cell. So if you don't want to type this from scratch, I can just paste the code in the chat here. So, and should already have the correct indentation. Okay, so here is going to be the function that delete all the links of the cell. All these will be inside the steppable class, yes. Okay, so this makes sure that you erase all the links that you have previously, but so far you have not created the links. To create the links, now you have to define the function self.createLinks. No, this has to be created inside the steppable. If it's outside, the steppable cannot call it, okay? So far, you have not created any links, so everything's symmetrical, yes. So, but on the inside the function to create the links, we're gonna break the symmetry and only make links to the right. Okay, so let's proceed to the next slide. Okay, so now we have to define this one. So let's, for example, go to line 33, and let's define the class createLinks. So again, I can, for your convenience, I can just paste the code for you on the chat. You have to make sure the indentation works. And now let me go through through it to show how it works. So inside the function create links, you have a loop over all the cells of type crawler. So you grab all the yellow cells. In this case, it's only one, but you can make a simulation with two of them if you want. Then, once you grab that crawler cell, you go over all its neighbors. So there is a loop over the neighbor of that cell, okay? And then you have a check if you actually are seeing a neighbor and not the medium, okay? So in the case where you have an open boundary with the medium, you cannot create a FP link between a cell and a medium. So that's important. That's something important to stress. You can create links between cells, a cell and another cell, but you cannot create a link between a cell and a medium because the medium does not have it's not really an object and does not have a defined center of mass. So the links can only be created between two cells, okay? You can create things like anchors that specify, create a link from the center of mass of the cell to a specific point in space, okay? That's something that is on the slides, but you will not have time to go over in this section. So you go over all the cells of type crawler, go over all its neighbors, you make sure that your neighbor is a cell, okay? And once it is a cell, you invoke this function here that can also be found on the drop-down menu, which calculates the distance between the cell and the neighbor. So that basically is going to get the distance between the center of mass of the cell and the center of mass of the neighbor. And it gives the coordinates in x, the distance in x, distance in y, and distance in z. Of course, because this is a two-dimensional simulation, there is no distance on the z-axis, okay? So that would be 0, but you have a delta x and a delta y, okay? So once you have the distance in the x and the y, you can get the angle by using this formula, this Python formula, @tan2, where the first end is going to be the y distance and the second it will be the x distance, and that returns a number between minus pi and pi, so it returns in radians, okay? So given that this is the center of a yellow cell, this is the center of the red cell disconnecting, right? You can get this angle here. So this angle is relative to the x-axis, right? So red has a directionality on it. Then the next line here, line 89, you just convert that angle from radians to degrees because it's easier to think in degrees, okay? And here is we take the absolute value of this angle, and what you do is that if that is within the maximum angle that you define at the very beginning of simulation, then you create a link between those cells. Then you use the self.new FP link, the cell that create the link, the cell that's receiving the link, the strength of the link, the target distance, and the maximum distance. Okay, so make sure that you have from math import star at the beginning of your code so that you can actually invoke the arctangent to function from the Python. Okay, so once you do this, I already pasted the code for you to add to your own version of the code. And once you do that, you should be able to see a simulation that looks like this, where the cells makes links and pulling the cells in front of it, so it keeps crawling to the right. Yeah, the more links it creates, the more it accelerates. Okay, so of course, if you make that angle to be plus or minus 180, you're going to create links everywhere, and then the cell will not move. Okay? If you make the angle to be very smaller, you only see a few of cells, so you will be movement to be harder, so you have to give an angle so the cell can grab enough neighbors so it can pull itself forward. Y to the right is just because that's what I said. It's just an, Kim just said, it's just an example. If you want to know why is to the right, given the code, is that X is defined to be positive in this direction, right? Y is positive here and negative here. So, and the angle that is given is going to be from minus pi to plus pi, okay? So the angles from here to here. So if I only check if the angle is in this direction, it usually goes to the right. Okay. So
Can this be dependent on a gradient as well? So could we define gradient and return something like an x and then put this into this formula?
yes, for example, you can, when you calculate your angle, you can rotate it by adding another angle here. So it can be your angle is going to be degrees of angle plus 90, for example, and that should make your cells move perpendicular on the x-axis. Okay. I think this will work. You can try in our code and see if now the cell moves on this direction.
No,
And
I mean,
this angle by which you shift everything can be a function of something else.
I mean, a connection between the two things. One is the gradient and one is this migration of the cell. So if we could have a gradient made by other cells and then we return something which defines the X error. So this something, can this then be integrated in this new formula?
Yes, it can. It can. Whatever value of this gradient is, so wherever this information is coming from, we're going to give you the preferential direction, right?
And then we just say X is whatever we return from our gradient producing simulation, and then we just put it here as an X.
Yeah, yeah. Or I would put here in the angle calculation. So I'll have this degrees angle minus, and that's going to be the angle at which the cell should move, and that should direct the cell along that gradient. So I'll put it right here as an extra addition here. There may be other ways to do it, but that's one possible way. But yes, you can do this.
Okay, thank you.
Ali, yes, you're override the maximum adjustment because you're doing that from the code. Actually, for this one that you can download, if you go back to the Python level, you see that the maximum adjustment is set to 0. Okay, so why is that? Because you do not want the CompCell player to make the links for you. You want to not make any links. So you set all the maximum of junctions to be 0, and you have the untag, the local tag there, so it allows to do everything from the Python level. And then at the Python level, you do whatever you tell the code to do. You cannot create these links. Well, links itself can only be between two cell types. It cannot be between a cell and a medium, but you can use something called anchors, okay? That's the next set of slides where you basically, okay, I don't have the code here, but I'm going to make the code available where you basically do the same thing, but instead of here specify a neighbor, you specify a pointing space, and this pointing space may be in front of the cell, and then the cell walks, also create links, but in front of it, okay? So the anchors make a link between the cell center of mass and a pointing space, and you can also do this to model cell migration. But for today, that's everything I want to show you guys, how links work, how you can make the links between cells of different types, and how you can control the links from the Python levels to do whatever you want to do, okay? So in the files, you have a code to see how you can use the same concepts to do a conversion extension of tissues. In this case, you're creating links on both sides of the cells. And if all the cells are pulling each other at the same time, you can generate contraction, conversion extension of the tissues. So the files are there for you to do. I'll put the files for the anchors as well. So you can actually do cell crawling with the absence of other cells as well. Okay, so with this, I will end up this section. Please fill up the questionnaire, and I hope this has been useful to you. What you're gonna learn tomorrow is how you can combine links and compartments to do things like tissue folding, or make the cells with different compartments, maybe elongate or shrink along a specific apical polarity axis, or make the cells connect with their apical sites and pull on another to create invagination folding. Okay, so that's the plan for tomorrow. Then Prion Adyapak, Dr. Adyapak, that's gonna teaching that to you. You'll be seeing me again tomorrow to teach dynamic compartments modeling in Computational 3D. Okay. Well, with that, I will thank you for your attention, and I hope this was useful to you. Please fill up the questionnaire, and let's take a break.
Yeah, so please do fill out the questionnaire. We actually have one hackathon lightning talk that we'll do in a minute or two before lunch here, and then we'll take our lunch break. But we'll give everybody a couple of minutes to fill out the poll. Omar, are you still wanting to do your lightning talk today?
Yes.
Okay, great. We'll have you queue up in just a minute here. So while you're filling out the poll, Julio will stick around for a few more minutes for any last questions. And then we'll go to lunch at about 2:05 today.
So the I still fail to understand what is the advantage of links over defining contact energy, because even with links you'll still have to figure out all the energies and relative strengths and so on and so forth, which is the same in contact energies. And in fact, as you said, you cannot add a link between cell and a medium, but you can add contact energies between cell and medium. So
Okay, one of the advantages of the links is that you can model things like cell contraction, apical constriction. You cannot link the cell with the medium, but one thing that cannot do is, for example, if you have a bunch of cells of the same type, okay, and you take the cells on the top layer and you just pull them, okay, to the right. The cells at the bottom do not care if you just use contact energies, because losing contact within the cell and replace that with the next cell is exactly the same energetically if you do that with contact energies. Okay, so only contact energies, everything is very slippery. Okay, you can take a cell, you can do this around it, and energetically nothing change if you just use contact energies, or you move with this one with another one here. But if you have links between the cells, moving this at the top layer of your cells against the bottom layer of the cells is going to be costly, because as you do this, those links here, if the cells are connected with links, those things are going to be, you start to be stretched along this direction, and that's going to generate then you have a shear force resisting the shear. Okay, so without the links, if you only have contact energies, the tissue is completely fluid and cannot resist any shear stress. Okay, so But if you have the links, then they're going to be a shear module. So doing this will be costly. So that's something that can be done with links, but it cannot be done with contact energies alone.
Okay.
Make sense?
Yeah, that example is
Yeah, the other thing is that if you push the cells, the tissue, well, if you push a cell, right, and deform it, there will be a cost to it, right? If the cell will not like, but you have a bunch of tissues or cells that only have contact energies between them, and they are all the same. And you push from the sides, okay, there's no cost for the cells to just rearrange and readapt to this new shape, okay, because they can easily slip past one another. But that will be the case if the cells are loosely connected, right? It's going to be easy to do this. And they not have stable cadherin junctions. There are only kind of steric interactions between them. But if the cell have stable cadherins, right, have tight junctions, then you can model this with links that will be more permanent connections. And then when you push the cells, compress cells from the side, then the cell will like to pass one another and squeeze, but they cannot. But then they will go start to stretch the links or compress the links, and then there's going to be resistance to this compression or the extension if you reverse. So there you have a bulk module, well, young modulus arising from it. Okay, so that's another example where you won't have links. Okay, so this will be just passive links. They just resist deformation or resist shearing. But as James said, it's a way to add solid-like properties on top of a simulation framework that by default assume that the cells are liquid-like. Okay. So by adding more links or playing with how easy the links can be rearranged, you can model things like glassy behavior of the cells, jamming, rigidity percolation, and this other types of properties that the cells have, the tissues should have.
Thank you.
You know, that's really interesting because, you know, I'm facing a problem with my project that is, I don't know if Julio remembers, but it's the porosity induced in nanomaterials by heavy ion irradiation. It's like material science. So there's a time, well, in the beginning, the bubbles start being created and the material, is around them. But after a certain dose, these bubbles start to expand a lot, and the material is not like material. It's not like a foam anymore. It's like more nanowires, and it was not possible to create nanowires in the material only having contact energy, but maybe creating links between the materials. They start to stand together even if they are being pressed by the bubbles. It's very interesting.
Okay,
it's a solution.
Maybe that's a solution. Yes.
Yeah.